which when you convert it is 0.05 kilograms per mole. Okay, but when 314 joules of is added as heat, the heat added is 314 joules. As related to a 30 gram sample. So the mass of the sample is 30 gram, which is 0.03 kilogram. The sample's temperature rises from 25 to 45. So the change in temperature of the sample is 20 degrees Celsius. What is the specific heat? So specific capacity, so its heat is equals to mass times C change in T. Your C would be the heat over the mass times the change in temperature heat. So your heat here is 314, M is 0.03, the change in T is 20. So specific heat capacity kulula ukusithola. So it's 314 over 0.03 times 20. So it's 523.33 joules per kilogram Kelvin, right? I think those are the units for C. Then would be but the molar specific heat. The molar specific heat is the same formula generally. But lona, instead of saying mass, it says number of moles tending T. This is mass specific heat esijwayele, and this is molar specific heat. Heat capacity. Molar specific heat capacity. So here it's gonna be 314 over the number of moles were 0.05. And change in T is the same change in T, and it's 20. So here you just change the 3 to a 5, which is 314 joules per kilogram Kelvin. Yeah. And then they say, see, how many moles are present? How can you find the number of moles? This is not per kilogram Kelvin, sorry, it's per mole Kelvin. With the molar specific, it's per mole Kelvin, different from this kilogram Kelvin. So, Mabati, find the number of moles present. The number of moles present would be the specific capacity, basically, less no mole, less over the specific capacity mass. Let me show you how is this possible, because more divide than the specific capacity less. What about unit? Joules per mole Kelvin over lawala phezulu. It's joules per kilogram Kelvin. The question wanted the amount of moles on it. All the other units can cancel out and we'll left with per mole kilogram. So you'll be left with the number of moles basically. Because yabona la mole bakunika grams per mole, that's what 2 grams per mole. Yeah. So I think we should divide the amount by, because this is over. So it's joules per mole times kilogram per joule. Consider joule kilogram per mole. Oh yeah, yes, divide that. Yeah. Divide that. Minutes la performing. So it will be 314 over 523.33. To find the number of moles, calculate 314 divided by 523.33. So it's 0.0006 moles. But the units more specifically would be grams per mole, would be kilograms per mole. Yes, kilograms per mole. And we are going to start how many kilograms per mole. We started off with 0.05 kilograms per mole. Look at how many were used up because this was the final amount. If this was a bigger number than the first one, then lo endo, you're wrong into it because you are suggesting that there was moles generated, which cannot be the case here because they have to be used up. Yeah. So that was number 19. Then we try number 20. Number 20, what's a container with a mass of 0.6 kilogram. So we have a container that the mass of container is 0.6 kilogram at a temperature of 20. Initial temperature is 20 degrees. When 2.5 kilogram of boiling water. Then you have water here. Mass amount is 2.5 kilogram. Temperature initially amount that it's boiling, so it's 100 degrees Celsius. But the final temperature of the solution is 90 degrees Celsius. What is the specific capacity of the container? Okay, so let's see a container. So this one is very easy, right? We just say the heat that is gained plus negative heat that is lost. So in terms of gaining heat between the container and the water in the temperature band, you want to gain heat. So the container is gain heat. So it's the mass of the container, C for container, changing T. Negative, let's lose the heat amount there. So it's the mass of the water, C for water, changing T. So the mass of the container was 0.6 C for containers for now. Changing temperatures from 20 to 90. So we find out 90 minus 20 is equals to mass of the water is 2.5 C1 is 4186. Changing T 100 to 90. So it's minus 10 here. The change in temperature because the final is 90. 90 minus 100 is minus 10. So you solve for the specific capacity of a container. It's gonna be negative 25 times 4186 and negative 10 over 0.6 times 7. So it's 24 negative 16.6 those we kilogram. You can probably divide by 1,000 and from the table to kilojoules per kilogram Kelvin by 1,000. You get 24 and then 9 kilojoules Kelvin Kelvin. Then, what mass of butter which has the usable energy content of, so energy at the butter is 6,000 calories per gram, which would be equivalent to change in the gravitational potential energy of a nematode. So we have a mass of a man here that is 73 kilogram, who ascends from sea level to the top of Mount Everest at elevation of, so the height is 8.84 kilometers, which is 8,840 meters. Assume an average kg 9.8 meters per second. But in what mass of butter? Okay, what mass of butter? So mass of butter, which has a usable energy content, will be equivalent to change. Oh, izolingana ngokwe-energy, izolingana imasa engakanani ezolingana nalo muntu owehlayo ngokwe-energy. So asicalculate i-energy yalo muntu-ke lo ascendayo from Mount Everest, because une-height, energy yakhe, potential energy angithi. So his potential energy is mgh with 73 times 9.8 times 8,840. 73 times 800 times 8,840. So potential energy I want to know is 516,256,000 joules. Wait. Yeah. I think I patched the calculator wrong here. Yeah. This is more like it. Ngibangela singaka 6,324,136. Yeah, 6 million joules. Makes sense. So what mass would be equivalent? What mass of butter would be equivalent to this amount? So kahle lana we know that energy and heat are the same thing. Heat is thermal energy. So heat is equals to mass times C times change in T. Lana, given the information we are given, the energy of the butter is 6,000 calories per gram. Let's convert it to calories per kilogram. I think, now we have to compare two energies. So I think we're dividing the other with the other to see how much mass would sustain this amount of energy. So imagine converted to joules. So it is 6,000 average joules. 25,000. It's 25,104. Okay. It's 25,104 joules. Yeah. Therefore, the mass would be 6,324,136. No, there's no comma here. Over 25,104 joules. 25,104 joules. Nobheka ukuthi mass engakanani engu-maintainer. 6,32 6,324,136 over 25,104. It's 251,92 joules kilograms and kilograms of butter. So it's a huge amount of butter. 250 kilograms. Ibhathe engasustain i-energy yomuntu owayo ku-Mount Everest owasendayo rather kule height lengane. Mount Everest is the highest mountain on earth, angithi. The highest point of elevation is Mount Everest. The deepest point is Mariana's Trench. Ngithola khona lama-fish lawa serious. All right, so that was number 20. Number 21. 21. Bathi la a 150 gram copper bowl contains 220 grams of water bowl. So the mass of the bowl, which is 150 gram, which is 0.15 kilogram, contains 250 grams of water. The mass of the water is 220 grams, 0.22 kilogram. The initial temperatures of both is 20 degrees Celsius. A very hot 300 gram copper cylinder. So you have the mass of the copper cylinder now, 300 gram, which is 0.3 kilogram. Is dropped into the water, causing it to boil. The water boils. So if the water boils, it means the final temperature is 100 and but the mass of the water that is boiled away is 5 grams. So the mass of the water that boils is 0.05 kilogram. 0.005 was divided by 1,000. All right. The final temperature of the system is 100. Okay. How much energy in calories is transferred to the water as heat? As heat, how much did the water gain? It's easy to look at that, because you have the mass of the water, the temperature change, so you can calculate how much heat it gained. Heat gained by the water, mass of the water, C for the water change in T. So the mass of the water was 220 grams. But then we can assume that the water that boiled away was the one that received the heat, Yeah. Oh, then the water gained two types of of heat. So that's it. Was for it to boil started from 20 to 100, and then my 500 boil. So they will now I have to include plus M and B. Latinate of vaporization of the water. And that mass right there is the mass that evaporated. This is the total mass of the water. This is the mass that evaporated. Because this part is talking about the evaporation phase, the 5 gram volume. So plus the mass that evaporated is total mass of the water is 0.22, 0.224186. The change in temperature of the water is 100 minus 20, so it's 8. Plus the 0.005. Fraction of population is 22.2 times 10 to the 3. And we will find the heat that is gained by the water. All the water. The first part the element evaporator, the part is S2. It's for the water that became steam. 4, 6, 80. 0.005. There you get 73,784.6 joules of positive heat gained. And then, but how much to the pole? Now the poles we calculated the same way heat gain in it. It's the mass of the pole, C of the pole changing T. Mass of the pole is 0.15 and 150 grams. C for the pole, what is a copper pole? So let's see specifically it's a copper material. Specifically it's a copper, it's 390. And the temperature of the pole, it changed from 20 to 100 now, so it's 8. But the pole did not change phase, so all this is 0.15 times 390 times 8. So this is 4,680 joules of heat gained by the pole. See, but what is the original temperature of the cylinder? The cylinder bayifakile laphaya. So sazi ukuthi copper, it's a copper cylinder, just like it's a copper pole. We know its final temperature, but the final temperature of the system is 100. So about the cylinder, what do we know? We know the mass of the cylinder is 0.3 kilogram. Its final temperature is 100 degrees Celsius. We see wow, a cylinder. It's a copper cylinder, so see why you have to see we pole 390 now. So now we want the original temperature. Okay, Lana to make you understand the heat that is gained by the water. The heat gained by the water in the bowl is equal to all the heat that is lost by the cylinder, the hot cylinder. But I found it hasn't seen the shiza. Uma ukhanda isoda, ama-China uma ukhanda amasoda, thatha isoda elishisayo, elibilayo elibuka lifake emanzini. Into enjalo-ke yenzekile. So yonke i-heat ezolahlekelwa ile soda ingana yonke i-heat ezogainwa ila manzi ngale bowl. Yabo? So it's equal to all the heat lost. All the heat lost by the cylinder. Cylinder will lose heat. The copper in the copper bowl in the water will gain it. So thina calculate the heat ezogainwa ile heat in the bowl and the water. Ilena lena ngithi. Calculate heat lost manje. Heat lost will be 4,680 plus 73,784.6. So this is the heat lost, well, it's the total heat gained. So it's 4,680 plus 73,784.6. So this is 78,464.6 joules. This is the total heat lost by the iron, by the copper, the anti-veshisal. Now we can find its initial temperature. The heat is mass times C times change in temperature. The heat to 7,864.6. Mass yayo it's 0.3. See why 9. then the final temperature sifunayo initial 1. Oh, final 100 initial sifunayo. So this is 100 minus initial temperature. You solve for the initial temperature, which would be it's 78464,6 over 0.3 times 390. And then what you're gonna do now, so minus 100 times, yeah, minus 100. Actually, it's minus 100s. Yeah. So what you're gonna get is 578. Oh yeah, I think you have to account for the negative here. Because this is heat lost, so it's negative. Yeah. The temperature is 570 degrees Celsius and the machine is very hot. So it makes sense. Initial temperature was 570 degrees. Very nice. So that was number 21. Yay. Ending number question. Let's try number 22. Particular ice is added to 1 kilogram lemonade, cooling it from 20 to 0. So we have ice now, we have lemonade. The mass of the lemonade is 1 kilogram. The temperature, the change in temperature of the lemonade is final is 0, so it's minus 20. Or 0 minus 20. So it's minus 20 degrees Celsius. How much ice melts? So when the mass of the ice that melts, but the heat capacity of lemonade is equal to the heat capacity of water. So heat capacity of lemonade is same as the heat capacity of water, which is 4186 joules per kilogram Kelvin. So Lana, it's an easy one. You want the mass of the ice and it. The ice never ate kule one nakuzani kule 1 kilogram lemonade. Since we have ice, Lana, we want the amount of ice that will melt, assuming that the ice change temperature. The ice uyazivele ukuthi kuzobe ne-ice nokuyifaka emanzini. Njengoba uyifaka kule lemonade fanele uyifake emanzini izomelta ngithi. Yeah. So it's final temperature yale ice nayo. Initial temperature yayo siyazi, but final temperature yayo u-0. It could be that the temperature change and it just melts. So it could be that stage. In fact, it is that stage, but mothathe ice uyifake emanzini, it only melts. Yeah. So the initial temperature of the ice will assume it's 0 degrees Celsius, and it is in its melting phase. It is in its melting phase. Yeah. So Nana will say the heat gained by the ice is equal to the heat lost by the lemonade. Heat gained by the heat gained by the ice is the mass of the ice, C for ice, changing T. No. The mass is not changing. The ice is not changing temperature, it's changing phase. So it's the mass of the ice times the latent heat of fusion is equal to The heat that is lost by the lemonade, it's the mass of the lemonade, C for lemonade, which is C for water. Because bashir ukuthi on times change in T. So the mass of the ice is just the mass of the lemonade, C for lemonade, change in T over the latent heat of fusion. So the mass of the lemonade is 1, C for lemonade is 4186. Change in temperature is -20. Yeah, it's -20. But lana, because lana we want the mass of the ice and the ice is gaining the heat, you have to assume positive, right? Yeah. But if you don't want to assume positive, njengoba bekakubuze lo mjede kade eklasini, you just add the minus. You see the importance of the minus. Manje usuzoba ne-negative mass. Uyakhumbula naseklasini besifuna i-mass negative. So that heat of fusion is 2, it's 3.33 times 10^5 negative la. So shaya konke lokhu calculator 4186 times 20 over 3.33 times 10 to the power 5. So you get 0.25 kilograms, which makes perfect sense. Yeah. So that was number 22. Number 23. Let's see how long. It's been an hour. Okay, I will try to go for 2 hours at least. For a long video and everything. But just push up. There are some, these questions again are all very important, so I'll try to do as much as possible. But like the name, I have the solutions to this last question and these 3. I have them written down. Maybe if you want to figure out one, I'll send them to you. Now let's continue. Number 23 now. So for number 23, but if 0.15 kilogram of ice at 0 is added to 0.25 kilogram of water at a temperature of 20 degrees Celsius. The question A is, does the ice melt? The answer is yes. It is at its melting point. Temperature is equal to 0 degrees Celsius. So it does melt. All of it will melt. B, what is the final temperature? That temperature is easy to find, right? Heat gained equals to negative heat lost. So what will gain the heat? The ice will gain the heat, right? It will gain the heat of changing the phase, and then gain the heat of changing the temperature from 0 to the final height. So the animal heat gained is the mass of the ice times latent heat of fusion plus the mass of the ice, C for water, times change in T. Remember, after this heat, the ice by month. And then this is the heat responsible for changing the temperature of the water from 0 to the final temperature. And then it's equals to now, what will lose the heat? It's the ice. It's the water, I mean. So now, but the water will only change temperature. mass of the water, C for water, change in T. Yeah. So the mass of the ice, 0.15, Latin rate of fusion is 3.33 times 10 to the 5. Mass of the ice, 0.15, C for water is 4186. Temperature change, final as initially the ice was 0. So this is just TF. TF minus 0 is equals to negative. Mass of the water is 0.25. C for water, 4186. Final temperature minus siyazi initially yawo 20. And you solve for TF. Solve for TF. So let us see what solve for TF. Hey, in there. I want to see what your final thing would look like for it to be it should be okay, so we can transport, we can divide we can multiply inside, I mean. So after that you'll have 0.15 times 3.33 10 to the 5. And then it will be plus 0.25 times 4186 times 20. Now it once you transpose it, ukiangalia kiputia as a convector divide the 0.15 times 4186 and then plus 0.25 times 4186. Yeah, I think it's over final answer. You'll find the final temperature. I'll leave this to you. Number 1, 23. Easy stuff. So number 24, when you make a bath, how many kilograms of hot water and cold water must you mix so that the temperature of the bath is 40? Total mass of the water, hot plus. Okay, this is one of those ones. They are fun levels in terms of the approach. You know, we are mixing. So heat gained is equal to negative heat lost. So when you make a bath, how many kilograms of hot water? It's 60. Lana nje heat izogainwa amanzi abandayo. So mass of the cold water, C wamanzi change in T is equals to mass of the hot water, C wamanzi change in T. Amanzi noma ashisa abantu ano-C oyi-1. So bayakutshela lana ukuthi the mass of the cold water plus the mass of the hot water is equals to 185 kilograms. Yakubona lokho. So sokusebenzisa lokhu somehow sisiya kule formula lethu substitute mass of the cold water sinawo but usiwa amanzi 4186. Change in temperature, but final temperature 40, so it's 40 minus 25. That's the cold water. Is equals to negative mass of the hot water 4186. It should be 40 minus 6. Oh, it's all simultaneously. Okay, so simultaneously. Should I calculate again? It's 4,186 times 40 minus 25. This would be 62,790 mass of the code water is equal to 14 minus 6. This would be 83,730 mass of the water. Yeah, second equation. And then you solve simultaneously. You know how to solve simultaneously, so now I will leave it to you. Yeah, these are relatively easy. I'm not why, but they're getting easier, you know. So that was 24, 25, 25. But ice at 10, -10 degrees Celsius and steam at 180 are brought together at atmospheric pressure in a perfect insulated container. After thermal equilibrium is reached, the liquid